and welcome to Data Engineering Explorers, and today we're going to explore data platforms. This is part 2, but it's quite straightforward, so perhaps you don't need to watch the part 1, but I would advise to do so. And the topics for today are data platform concept overview, then we're going to compare data warehouse, data lakehouse, and data lake. Then also understanding the concepts and differences between table format and file format. And last but not least, we're going to go through some Spark core concepts and understand its role as a store engine in a lakehouse. So the first topic, data platform concept overview. So as we've seen before in other videos, data engineering takes part between analysis and other data products and data sources, such as here we have an e-commerce, and here we have a dashboard as a data product, and we have data engineering here in between. But what does it mean, data engineering? We have a data platform that makes able for data pipelines to run and to create data in a format that makes sense for analytical reasons, such as dashboards. And these pipelines, they are basically in this format, but I should say that these are for batch, mini batch, and micro batch, because if you're using streaming data pipelines, you probably won't need a scheduler. But as this is not, we're not focusing on streaming because it's just in specific cases you should use streaming, as it's quite expensive and may require some more maintenance than batch pipelines. I would suggest you look into batch, mini batch, or micro batch. But here we have the ingestion part. You would need to retrieve the data at a certain time, in a certain window of time. For instance, micro batch, you may use a minute, 5 minutes, mini batch 10 minutes, 1 hour, and batch once a day, for instance. Then you would transform this data, then you would store it, perhaps store it before also, it depends on what you're doing, and make available for querying or data products, as we have mentioned before. And also it's important to know that this structure for data pipeline can be used for structured data, semi-structured, and unstructured data. And okay, now we know about how data engineering plays a role, and also what a data platform is, what are data pipelines. But let's go back a bit and understand, maybe more aligned with data platform. So what is data infrastructure? What consists of? And we can say that it consists of automation and storage. And I also have a video explaining that more in depth, maybe for people that aren't aware of this concept previously, but I'm gonna link it below. But going back to the concept, here on automation concept, we have compute engines. That is orchestration, ingestion, transformation. All of this is considered the automation part of data infrastructure. And we have here also the storage engine, because the storage engine is basically an engine that will automate some transactions made in stored data. And the storage part is basically the file format, the table format, and catalog. So this is the data itself, and this is what manipulates the data, right? So if you look at a data platform, a data infrastructure, that's what's basically it consists of, right? And also a little reminder that when looking into data infrastructure, you need to evaluate cost, as some of these tools, especially services from clouds, can be very expensive, especially if you have loads of data. And yeah, I would strongly advise to look into that. So, okay, looking at this diagram here, in the last iteration, if you're not aware, we have explored one base data infrastructure, and the idea is to iterate through it and have improvements, so it has more and more value. And we have used Python, Airflow for orchestration, ingestion, requests. This is a library in Python, and also pandas. And for storage, we used S3 and Parquet, only a file format inside storage. And for this iteration, we're going to look into table format, catalog, and storage engine. As you can see, they are the last parts that we haven't looked into. And I'm saying this because these concepts that I have just shown, they will set the foundation for the whole video, and also this will make you understand that this is actually the goal for the rest of the video, explaining some concepts related to table format, catalog, and storage engine. So when we start implementing it at the next set of videos, it is quite clear why some things happen, and actually the concept itself it isn't just a tutorial. You understand the concept behind it. And as you can see, let's go back a bit. As you can see, the biggest difference, the major difference here is table format and storage engine. So it's related to storage, right? And it is actually related to this concept only. And this will get clearer as the video go through, but I just want to point out that now, because yeah, so pay attention. ACID transactions, what that is. Transactions are basically read, write, date, or delete your data. So when you read it, you're doing an ACID transaction, or at least you should. You're doing transaction, actually. Yeah, the ACID part is what we're exploring now. And ACID stands for atomicity, consistency, isolation, and durability. And these concepts, I'm gonna go through these concepts, but they are very simple concepts, but at the same time they can make a huge difference, because if you don't have them in your storage, you're going to have trouble later, very, very possibly. So what is atomicity? The entire transaction is executed, or none of it is. So you can see here that you have state 0 and state 1, and let's say this is an aggregation of your data, transforming into a new column. Okay. And if the transaction starts being done and it happens some error here, you don't get like half of your table. Let's say we have it the whole here and we have the error here, and the result isn't the half that worked. you don't have a result, or you have the whole table transformed with this aggregation, right? So this is atomicity. You have consistency. Consistency, it is basically transactions only make changes to table in predefined, predictable ways of allowing rules and constraints. So let's say you want to sum both two fields, and the second field actually has like not necessarily it is not necessarily all int information. So we were expecting 2 ints, and something happened, that column isn't clean, or it isn't forced, let's say, to be int, and you have some kind of problem, and it stops, right? The transaction stops because ok, vamos voltar aqui que tá ruim. So consistency, that's basically transactions only make changes to tables predefined and predictable. Blah, blah, blah. About consistency, the second acid transaction. The transactions only make changes to table in predefined and predictable ways. So you expect something to happen, and that allows rules and constraints. And okay, we have the drawing from the last one here, and the error here happens because of some rule or some constraint. And this can be expecting some kind of type, some data type. Yeah, that's a good example for this. You have isolation, the third one. If multiple transactions are executed at the same time, they don't interfere with each other. So if you have multiple reads, you don't interfere with that, with each other. You can have multiple people accessing the data and making multiple and different writes and reads, and the transaction should be able to handle that. The table should be able to handle that. And the last one, durability. It ensures that the transactions are executed even on the event of system failure. So even if the system fails for whatever reason, the transaction is executed. That's it for ACID transactions, and ACID transactions are actually a big thing while handling data, because as you can see, there are a bunch of small things. For instance, when you do an action, you expect it, you perform an action, you expect it to be applied on your whole table, and if not, that can cause a lot of trouble. You have to go back to it, and that's not very productive because you want your data pipelines to handle all of it. And these concepts are quite important, especially when it comes to the next topic, because data lakes usually are ACID compliant, and yeah, that's a big thing, and maybe I'm anticipating myself. Let's go to the next topic. Data warehouses versus data lakes versus lakehouses. Okay, first of all, we have data warehouses. Data warehouses, this data warehouse diagram consists basically of structured data sources, as you can see, an operational system, a CRM system, and you have ETL tools, not the focus here, but usually very straightforward, only connecting the source and dumping it into the sink. And the sink here is actually the data warehouse. That's the focus here. And this data warehouse can have destinations such as reports and dashboards. So the data warehouse actually only this structure, and I would say, for example, you have MySQL and you have BigQuery, maybe Snowflake too, as examples of this structure. And only this specifically has the compute engine, the storage engine, the catalog, the table format, the file format, and the storage itself. And many of these things you have no idea that it has because it's so coupled. It has many layers, and you only interface with the storage engine. So yeah, that's basically it. It's a very coupled solution, and it can handle structured data well. It works great with business intelligence because it has structured data that's required for dashboards, right? But you have storage at high costs exactly because it is a black box, let's say, and you have storage with high cost because you don't have to handle a lot of these parts, and it's a rigid system, but it's ACID compliant. As I said before, in another moment, you have great importance on ACID compliant handling of the data. Next, we have Lakehouse, data lake, and you have different kind of sources here. You have structured sources, but you also have images that is unstructured. You have semi-structured also. I put here APIs because usually they retrieve data. The data retrieved from APIs are JSONs. And you have many pipelines. I put here as extract load, transform load, but you can see, you can understand this as data pipelines. And you have storage for many layers, usually bronze, silver, and gold, or raw. I'm gonna put this one, trusted, and refined. Sorry for my writing, but you have storage, and you have inside storage you usually have file formats. They are usually stored in a way that the data is partitioned. For instance, every day you retrieve data, so you have data partitioned. That is having folders for each of the dates that you retrieve data from. And you have here the raw data, the trusted and refined. Maybe I didn't need to write it up here, but you have the catalog. And this is actually something that most companies don't do, and this makes a mess because if you don't have catalog what data you have in each layers, you lose control of it. And when you need something, you have to explore it, maybe open a Jakarta notebook or query it, but you'd have to search for it instead of only looking into a catalog. But you have the query engine. Maybe the query engine is actually linked directly to here. You have some services that do that. For instance, you can read Parquet files with AWS Athena, but I would strongly advise, if you're looking into building a data lake, to look into catalog. And you have destinations. I even put here different blocks for the destinations. So data lakes can feed data for ML models, AI, and also dashboards. So it depends on how you structure your data and what is your data, really, because you can't put images You probably can, but it's not very used. It's not a common use case, but you can put images in your dashboards, right? Image data. So that's basically it, and you can see that this structure, the difference from warehouse and lake, is basically decoupling all of the structures. So instead of having all of those features that we listed in only one service, let's say, you have it in multiple services. So here we have for data for storage and file format, you have it on one application, let's say. You have catalog as another, and the query engine as a compute engine, and perhaps a table format. It depends on what query engine you're using, but you can see that the data lake has it is very flexible. I would use this word to describe the main difference between warehouse and data lake. The data lake is way more flexible. It can handle well semi-structured and unstructured data, and also can handle structured data. It works great with machine learning and AI. It is cost effective on storage because, as I said before, usually data warehouses have high costs on storage. It is flexible and fast, but it's not ACID compliant. So you saw here where we need to improve, right, for the next iteration, where data engineering had to look at. Because you can see here that it can handle structured data. You can store your data in file formats such as Parquet, Avro, and other file formats, but this had some disadvantages as it isn't ACID compliant. So for our next iteration, let's say, and when I say R, I say data engineering iteration, because and I didn't give this context, but it started with lake warehouse and went to data lake, and now upgraded, let's say, to Lakehouse, the data platforms architectures. And yeah, you probably knew that because you were watching a data engineering video, but if not, that's the timeline. And here we have basically the same. You can see that nothing really changed except for this table format. This is the key to the next iteration, to the next architecture, because actually I put here differently also the extract to upsert because of ACID compliant. So instead of archiving, storing your data into file formats, it was created some kind of framework known as table formats. You have multiple, I'm going to go through them also, but you have this concept of table format that was it changed everything for data lakes. It actually changed to lake houses. So and you can have ACID compliant transactions because of it. So here we decouple a little bit more. We have something that we didn't have before on data lakes, that is storage engine. And let's remember that storage engines are the ones that are able to do ACID compliant transactions. And you have here also not only storage and file format, but you have also table format. So lake houses, they handle well structured data, semi-structured data, and unstructured data, so all kinds of data. It is suitable for data analysis and data science, dashboards and machine learning, let's say. It is cost effective, such as Data Lake was, and it is flexible and fast, as Data Lake also was. But as I said, the main difference is ACID compliant. It is ACID compliant because of table formats and storage engines. And we can say that Lakehouses are the best of both worlds because it has great management features, the table formats, and it is scalable and agile, such as Data Lake was already. So we have here, actually, the main difference is table format and storage engine. And again, maybe I'm saying this too much, but this is to emphasize the difference, because I see many places you have concepts of what some Lakehouse formats are and etc., but people don't understand what's the difference between a Lakehouse format and the file format. And I say Lakehouse format because some people use it instead of table format, but I think it's more suitable to use table format. Nonetheless, it is just a name, and you have this main difference. You have storage engines making ACID transactions to table formats. So you have, there you have it. That's the difference. That's the only thing you need to know between the difference between Lakehouse and Data Lake. The next topic is actually what it is different from a table format and a file format, because we have said that the table format is the main difference from Data Lake and Lakehouse, but what it is actually. Okay, let's give some names, and maybe it's clear for you already, but I'm gonna go through the concepts either way. We have here some table formats. We have nowadays Data Lake, Iceberg, Apache Iceberg, and Apache Hudi. These are all table formats, and we have file formats. We have JSON, CSV, Avro, ORC, Parquet, and all of them that have different structures, such as CSV, it's comma divided, and it's quite near Excel files, sheet files. You have Parquet that is column oriented, and you have Avro that's row oriented. So you have a bunch of files that are different, and we have the table format that have each its specifications, but them all have ACID compliant. They all are ACID compliant. And this is actually the structure of a table format. Actually, this is a structure of a Data Lake table format, sorry. And it is consistent of, you have a concept of a table, you have a folder here that is a table, and you have its metadata and its data. So that's the main thing between storing your data as a file format and as a table format. The table format has a big emphasis on metadata. So for each, for instance, ACID compliant transaction, you have a file. For each insert, for each whatever, you have all of the transactions executed on the data, and you have the data actually here. You don't have it exactly like this. Maybe depending on the table format framework, you have different kind of partitioning, and yeah, but this is only an example. And you have, so the table format consists of table, metadata, and its data. And you have here the main difference between a table format and a file format. If it wasn't very clear yet, I hope this makes it clearer. The table format has it all, right? All of this consists of the table format, the metadata and the data, and the file format is each one of these files. So you have here two kinds of file formats. You have a JSON and you have a Parquet, but each one of them are a file format. And you have differences in storing the data between when you use table format and file format. So here you have the table as I have the table format as I have already gone through, but you have the metadata and the data, and you store it on different partitions and etc. But here actually we have this file format. It is example. It's actually compliant to the Hive table format, I believe, but the Hive table. You have here for each partition you have some files, but for example, let's say you have a column data, and if the value is 1, you have all of the files that the column data equals 1 is here. So to make that more clear, for instance, if you have yesterday's data, it will all be here, and today's data will all be in the same partition. So why is that not good too, right? Because when you select data from your table, when it has a Hive format, in this case, you have to, and you have where x equals 1. And in this case, we have the partition as data. So the partition not being x, you have to go through all of the partitions to find all of the data that have x equals 1. So let's say in here we have a row that has in here 2, and here 2, and here 2. So you have to retrieve data from all of these files. And this is a pretty small example. Imagine if you have a database of data stored about your users, and you have, let's say, I don't know, 1,000 users, and you want to get a specific location user. So if you want all of the users that are in the US, you have to go through all of the 1,000 users to see what location they are, because if the table isn't partitioned in the location column, which is probably not. So you have this problem, right? And when you have a table format, you have the framework of it that has access to all of it has files, and it has engines that already do that for you and make queries optimized. So you don't have to go through all of this manually, because the framework probably does something like that. But when you're doing this, when you define a table by yourself, you have to do this. You have to go through all of the data, and you have to optimize that query afterwards. When you're using a framework, you don't have to care about that. You don't have to not care, but you don't have to worry about that. So you only query the table as you would query a table in a warehouse, and that's it. The framework takes care of the optimization of the query and looking into its partitions. So, iterating that again. Instead of manually configuring the querying and the storing. So if you store the data like this, you have to define the column, see which column makes more sense. You have to define it, you have to make code for storing it in a certain way. And upserting data, that's a big thing on this. You have to, when you have to update data, you have to go through all of these too. So instead of going through all of this, you have only the framework having the new transaction here and updating the metadata that is here. So if this is getting quite confusing, please let me know and I'll make another video on that. But this has this checkpoint. This file has all of the files that are actually in this time. At this time, you have all of that data. So for instance, if I did a bunch of different transactions here, I updated some rows, and I actually don't use these two files anymore. So I have the files of my checkpoint would have let's say we don't have file 1 and 2, so we have 3 to 10, and this would be on our checkpoint saying, oh, as you have updated your data, you have inserted data on other files, and now your data in its current state, after all of these transactions, you only have, your data consists of the files 3 to 10. So that's quite complex to do it manually. And that's why it's interesting to leverage table formats. Instead of manually configuring all of the use cases, I just said 2 of the use cases, inserting data and querying it. But you have other use cases that you have to take into consideration. So instead of doing that manually, you should consider it at least using a framework and leveraging its features. So some of its features are the clear definition of a table, because sometimes that's quite hard. When you have a data lake, you don't have a clear definition of what is a table. It allows time travel, right? Because you have the data stored when it was in its first iteration, and you have each of the ACID transactions that was executed, and you have each of the checkpoints that it had. So you can go back and say, oh, I want to compare the data from our users, how many users we have, whatever, and from the first quarter of the year, and the last quarter, and you are able to do that because you have time traveling here. And when you look at this format, it's quite complex, but when you look into the command itself, you only have to you only have to pass some parameters to use time travel. So this seems more complex than it is actually. So yeah, that's it. File formats are simple and they are necessary, but table formats are much more sophisticated. They allow ACID compliant transactions, and yeah, I would suggest you highly to look into that. Okay, onwards to the last concept, Spark core concepts. So for Spark core concepts, we're going to explore the topics of its architecture. We're going to go through an overview of its architecture. Then we're going to do a deep dive on its data structures, and we're going to look into Spark as a storage engine. This is for the Lakehouse format, right? The table format. So, architecture review. Spark has a goal to be a unified engine designed for large-scale distributed data processing. And its four key characteristics are speed, ease of use, modularity, and extensibility. So what does that mean? You have speed. You have Spark leverages the hardwares, the CPUs and its memory, to do multi-threading and parallel processing of the data instead of doing it serialized. And the query computations are directed acyclical graphs. That is, you only have onwards, and it's directed, and it doesn't do this, right? It doesn't go back. So you have this kind of structure. This is a simple example of what is directed acyclical graphs, DAGs, let's say. And here we have the one illustration of how the speed is leveraged. It's made. I'm sorry, and how it leverages some of the Spark concepts. So. You have the interface, the driver, the interface with the user. It's how the user is going to do. And when the interface sends a command, Spark creates an execution plan, and this execution plan it consists of stages, and these stages consists of tasks. So the stages are operations based on a plan, serial or parallel. So you may have a stage that comes before another stage, but when it's parallel, you have the tasks. That is the unit of execution. Actually, you can have stages parallel too, but yeah. So you have it in serial or parallel operations, and inside of each stage you have the unit of execution, the real steps that are going to be executed per stage. And this you can see in this drawing both concepts that actually make able speed, right? The parallel processing here you can have also in the stages, as I said, the jobs, and you have the directed acyclical graphs. That it's exactly this, especially in stages, because you have stages serialized and you have stages parallel, right? So yeah. Next, you have ease of use. You have data structure abstraction. So you have the resilient distributed data sets. That's the base, RDD. Just remember RDD. This is the base of the data structure for Spark. But you also have data frames and you have data sets. And this data structure abstraction makes able to be very easy to use Spark. And I'm going to go through this in the next topic, but that's basically it. And also you have simple programming model with some transformations and actions. So you can perform in, let's say, RDDs, you can perform transformations on it and actions. So you can I have an RDD here, and I can some column of it, or I can map something. So that's quite simple command, right? And you have the transformation that for instance map is quite sophisticated, right? And you have also the actions such as count. I put here count only, but you have the count. You know how many rows there are in this RDD and etc. So it's quite straightforward. You have data structure abstraction. You can perform transformations and actions on it. You have the modularity. As I said on the first slide about this Spark core concepts, you want to unify an engine for large-scale data. So for that, you have to have multiple programming languages. So that makes easy for the user. You don't have to learn necessarily a new data language just to use Spark. You have multiple. It is a unified library with multiple modules, such as Spark SQL. This one is the one we're going to explore the most in this course, video series, I don't know, and Python. But going back, you have Spark structured streaming for data, streaming data. You have MLlib, that's for machine learning, and GraphX. And it enables, because of having multiple programming languages and multiple modules, you enable diverse solutions, right, regarding data. And the last topic of Spark, key factors, key characteristics, is its extensibility. It decouples storage and computation, because previously what existed was Hadoop before Spark. And Hadoop couples storage and computation, so you have to use both, right? You don't have, but it was common. And as it is more interesting to have only one focus, because then you have a better tool for one specific thing. They did that, and they focus on computation, and you can use data stored in various sources. So for that, actually Spark has a lot of sources it can use. You have here some, but if you count the community plugins, you probably can use any kind of source with Spark. So you make able the extensibility of storage you can use, and you have a much better computation tool. Okay, now deep diving on data structures. You have here the same drawing about data structures, but basically you have RDDs that are more high level, and you have to set more things on RDDs. When you want, for instance, structured data, you have to you have to force, let's say, it, and then based on RDD and based on how people were using it's the data structures, they created data frames and data sets. And okay, first going to RDD concepts, and then we're going to go through the other structures concepts. RDD has three main concepts: dependencies, partitions, and compute functions. And this will make very, very understandable of why it's so simple and it's so good, the data structures. So dependencies, you have instructions to be constructed, the RDD. You have, for instance, if I have an RDD that is made with another RDD, I have this instruction. You have first this RDD1 as base, and you have this transformation. So That's the dependency that we're talking about. The RDD is constructed based on instructions. And when you're executing these instructions, you split the work to parallelize computations on the partitions. So, for instance, if you had the same situation as here, you would get the RDD one, and you would have its partitions, data partitions, 3 in this case, and you would partition the execution. So you have 3 executors for it. So you have the partitions being leveraged to be executed quicker. And last but not least, you have compute functions. So, for example, if the instruction is to change this, in the first case here, I have if x, I want to substitute with y. So whenever in RDD1 I have the value x on column 1, I want to substitute it with y. I will do that, right? This is the instruction of the transformation here. But in compute function, this is clearer why the partition and the dependency can be leveraged. So for its partition, you have an iterator, and this is actually the instruction for each of the partitions. And if I have, and RDDs are partitioned wisely, so if I have all of the x valued columns here in this partition, I would only have, actually I put drop here, but for the sake of the example, please think of sub, let's say sub here, but not necessarily that, but you get this part only, and you only change this one, because the instruction is specific, and you can alter just the part that makes sense to alter in this case. So here you have way less computation. You leverage the partitions, and you leverage the instructions to have less computation, and in consequence of that, less cost, less time, less processing. So that's very, very wise and very, very sophisticated. And okay, going back to the first diagram on data structures, as I said, we have extensibility, modularity, and you have multiple programming languages, and RDD is available in all of them, and so is data frames, but datasets aren't. So that's why we're not going to look into datasets, because we're going to use Python, and it is quite interesting, but it's not the focus here, so I'm not going to look into datasets. But okay, what are data frames then? If we have RDDs and they have all the awesome features that I described, why do we have data frames? Because as people who were using more Spark actually started to rise some other tools such as Pandas, and Pandas has a concept of data frame, and the data frame is basically the same thing as a relational database table. So Spark did the same. You already had Spark SQL, and this Spark SQL now has an data abstraction similar to the relational database table. So you have the concept of a table again here. So you can already see how does this fit with table formats. So the differences between RDD and data frames. You have RDD, that is distribution collection of elements, and you have structured and unstructured data. And data frames are a distributed collection of data organized into columns. So you have this organization into columns is the actual difference, because you have then the data concept very close to the relational data database table, and you handle well structured and semi-structured data. So data frames don't handle unstructured data, not at least before being transformed. Then you can transform it in structured, and then you can handle it with data frames. And the schema is necessary. So even if you're using semi-structure, for example, JSON, you have some columns here. You would have to create a schema saying, oh, this is column 1, and the type is int, and so on, while creating a data frame with the semi-structured data. And another key aspect is the diagram shows that the RDDs are the base for datasets and data frames, but I want to highlight that again, because data frames get decomposed into RDDs when executed. This image is from Learning Spark 2.0, a book, and you can see here how it gets decomposed. I'm not going to go through that, but because it's not the focus of the video, but I wanted to highlight that because even though our data frames can seem, let's say, better to handle data that is usually used on companies, they are based on RDDs. They are an upgrade, and when they are executed, they get decomposed on it. Okay, last concept on Spark core concepts. The concept we wanted to arrive, right, when thinking of table formats and lakehouses. So how all of this relates to storage engines and lakehouses. Instead of manually configuring, use a framework and leverage its features. I said this before, but we have a huge problem when it comes to data lakes handling data. And instead of handling it all by yourself, doing code for that, you can leverage Spark SQL as a storage engine and handle frameworks such as Iceberg and the Auto Lake. And I wanted to highlight here, when thinking of data warehouses, relational databases, you have SQL and you have the relational database table. So whenever you query it, whenever you say alter it, insert data, whatever, you have to use SQL to do so. You have this store engine to alter your table concept. That's exactly what Spark does with open source table formats. So by having this, you have a very strong concept of using ACID compliant transactions with open source data tables, data tools. This is open source, because you have open source table format, and you have open source compute engine, store engine. And here you would have a black box that you would have to pay a high price for it. So that's beautiful. And saying, going a bit more deep on it, you have some open source table formats. Have, as I said, Data Lake, Apache Hudi, Apache Iceberg, and you have Spark. You have Spark SQL. That's basically running Spark. If you have never seen it, running SQL inside of Spark, it's the same thing. And you have PySpark. I said PySpark because that's the tool we're going to use on next videos. And handling data frames. Data frames that are, again, abstractions of tables in databases. And the same thing here, abstractions of database tables, relational database tables. So you have both things here, open source. And okay, we went through a lot of these concepts, right? We went through a lot of concepts, a lot of things. So what's next? As I have said before, the idea here is to build a data platform together. And I'm gonna link below the first videos. Actually, I'm gonna list the playlist. And there you have all of the videos regarding this. And the idea is to build a data platform and improve its practices, such as we're doing now, looking into Lakehouse concepts, or at least concepts that lead to understanding how Lakehouse, what is Lakehouse, how to use Lakehouse, and to deliver more value, and do that iteratively. And yeah. And you have here our next steps. We have storage as an S3, compute engine as Python, as we were already using. But now we're going to iterate on it. We're going to improve it with a storage engine, Spark, as I said, Spark SQL and Spark data frames, and table formats. They are Data Lake, Apache Hudi, and Iceberg. So, again, about our platform. The base platform is done, and this is the part we're ongoing. We covered in this video all of the concepts we are going to need on Spark. What is Spark? Its architecture, how it leverages some things, and it's how it handles data, and also what is Lakehouse, how Lakehouse came to be, and what why exists Lakehouse formats, table formats, and what is table format. So we know all of this. Now we're going to implement it. That's the easy part and fun part, right? So that's it for this long video. I hope you enjoyed it. I hope it brought some light on some concepts that I myself have struggled with in the past, and I hope I made it clearer for you. I hope it is quicker for you to understand these concepts. And for next videos, we're going to implement it, and we're going to really see it working, Spark with Lakehouse formats. And for that, just keep up with us on Twitter. Actually, now it's X, right? I have to update this slide. But Twitter, YouTube, please, if you liked, give it a like, subscribe. This helps the channel. And with GitHub, we have all of the source code there. So if you're interested, please give it a look. And yeah, that's it. Thank you very much for staying until the end.